Today we're going to finish up this unit, which is wonderful. So let's get started. As a quick reminder of what happened yesterday, I want you to read the question, take a minute, pause the video if you need to, and figure it out and answer to what's on the slide. Great. The first step is to figure out what the chemical formula of vanadium 3 chloride is. The 3 here, don't forget, means that the vanadium has a 3 plus charge. Chloride, we find on the periodic table, has a -1 charge. So crossing them means that we get a chemical formula of VCl3. This VCl3 is going to be a product of a neutralization, yielding to vanadium 3 chloride and water, and the question is what acid and what base. Remember that the acids are characterized by the presence of hydrogen ions and the bases by hydroxide. So what we're going to do is we're going to pair up opposite charges to make neutral chemical compounds. So H plus Cl minus, that was going to be a 1-to-1 ratio, and the vanadium is a +3, but the hydroxide is a -1. So to get a neutral compound, we need a 1-to-3 ratio. We could balance the equation from here, but that wasn't the question. So the acid is hydrochloric acid, and the base is vanadium 3 hydroxide. For today, I thought it would be interesting to, well, I'll put it this way. The acid-base unit culminates in an application, and that's really what we're looking at today, an application of everything that we've been learning. So what you can see above me is a chemical reaction producing some brown gas. The important part to note here is there's a nitric acid, there is some copper metal, and there is a gas release too. This brown gas is nitrogen dioxide. I love this demonstration. What ends up happening is if you let it run a little longer, you get a backflow. It turns a vibrant blue color. It's wonderful. But the point is that acids are very reactive, and in nature, when you will find things like copper metal or other substances, the acids will actually do things like that, which is not great. That brown gas is pretty poisonous to humans. And so what you will see is in nature, there is a vast field of work in environmental chemistry, particularly in the realm of sampling. And what we have here is people are going into a river and sampling the water to measure the pH, measure the acid content, the base content, what you have. The person's wearing on their back a lab kit that will take some samples and maybe measure some data. But more commonly what you'll see is something like this picture in the middle, where the samples are sent to a lab and someone performs an analysis. And this item, I picked this picture because this item in the middle of the picture is actually directly related to what we're looking at today, I believe. Those are burette clamps. And so we need to talk about how you can chemically measure the concentration of an acid or a base in a chemistry lab. And the way you do that is through a process called titration. So there's the definition for you. It's a little bit to digest. I pulled the definition straight out of a textbook. It's a lot of words, so I want to kind of break it down a little bit. What you end up having here is the person who is the chemist will have a sample that is something's unknown about it. It's determining the concentration. So your sample, you have known volume, unknown concentration. And then you take a reagent, a chemical that you're going to use to react. You have known concentration, and you measure the volume. So the idea is you have a known volume of your unknown sample, and you measure the exact volume, where it's written there, the smallest amount of reagent of known concentration required to bring about a given effect. So the smallest volume, you measure the volume of your known substance to get a complete reaction. Yeah. The point is It's a complete reaction, exactly. No more, no less. So it's nice. It's this. It's you're conducting a controlled reaction where you're specifically measuring the exact amount, and using those exact amounts, you can go back and figure out this unknown bit here. That's the whole goal. We're figuring out the unknown bit of our sample. A couple more things to talk about. What we have here is a one piece of new equipment and several pieces of old equipment. Like I said, the burette clamp, the burette holder was exactly why I picked that image, but I wanted to pick one that was a little bit easier to understand. What we have here is a burette. That's the glassware. That's the tall glassware. If you'll notice on the picture, there's a 0 at the top and a 50 at the bottom. So the idea is that you fill it with liquid and then you drain it from the top to the bottom. So you fill it with liquid before you get everything going, and then when you're ready, you open up this thing down here is called a stopcock. You open it up, and liquid drips out. Right now, this is set to open because the way it works is you can rotate this piece that I've circled, and if you rotate it so that it is horizontally aligned, that would be closed. So that would look something like this, and you would just see, it would be rotated so you couldn't see it because it would be like in the plane or going into the paper. But you read this from top to bottom, as I said. So if you had filled it up, you don't have to fill it all the way up to 0. You can fill it up to whatever you want. But if you had an initial of 10 milliliters and then you drain it, and then when you have a complete reaction, it's at, 35 milliliters, the volume delivered would be 35 minus 10, or 25 milliliters. But the goal is these instruments. The burette shown is actually not great because it has lines every 1 milliliter. In the lab, you will use usually they go to the tenth of the milliliter, so that you can estimate to the 100th. It's a very precise piece of equipment. Oh, I made that picture too big. With a small aperture and stopcock, liquid or gas received or discharged. There we go. Oops. But then yes, right down here we have the volume, the Erlenmeyer flask that we're used to seeing. There'll be an indicator in your sample, and we use a graduated cylinder usually to measure the sample. This is not the known quantity, not the reagent. We're going to use a graduated cylinder to pour into the flask because, as you remember, flasks do not measure volume very well. So let's just go through the process really quick. I've got a couple more words to put there. I'm going to add a couple different words. Instead of talking about reagent, we're going to label them separately. So what we have here is our analyte. And the analyte is that sample, that unknown that we'd be bringing. So one, measure the analyte. And of course you want to record it. Two, add indicator. Since this is an acid-base reaction and we want to know exactly when the reaction is done, we can't tell that with our eyes. For example, in our pretty standard example of a neutralization reaction, you've got three options. If you're just pouring sodium hydroxide and hydrochloric acid together, you've got three options. You either mix them and there's too much HCl and it's still acidic after they've reacted because there's extra HCl. You pour them together and there's too much sodium hydroxide and the solution is now basic because there's extra sodium hydroxide left over. Or if you did it just right, they perfectly cancel out and you're neutral. That said, a hydrochloric acid solution is clear and colorless, and so is a sodium hydroxide solution, and so is salt water. So you have no indication that you're done, which is why we need an indicator. So in this case, what we have here, I believe this is bromthiamyl blue. And the reason I'm guessing is because if the analyte is an acid, bromthiamyl blue is yellow, and if it's a base, it'll be blue. So the process is that you add an indicator, you see your initial color, add titrant dropwise until endpoint. Now I understand that bromothymol blue turns blue at like a pH of like 7.6 or 8 or 9 or something, which you might think is too far, right? Ideally, through neutralization, if we get a perfect neutralization, we should have a pH of 7. There's a small problem with this process, and we all acknowledge it as chemists, be getting into it. The point is, while we may have overshot slightly, we wouldn't have known otherwise that we were done, which is why we're going to overshoot slightly instead of overshooting a lot. So you're adding the base, in this case, in the titrant slowly, and then you'll add a bit and it'll still be yellow, and you'll add a bit and a little bit of blue will be there, and you mix it up, and the blue goes away and it turns back to like it's just yellow, and you add a little bit more, and eventually what's going to happen, it's going to start to be this, like for like one drop it'll be green, and if you added one drop more it turns blue, and then that's when you're done. You turn it when at first appearance of blue, we're done. Sorry, I should add another step here because I forgot something. So I'm going to erase this. You add indicator to analyte. That's our titrant. We need to measure the initial volume for titrant, add titrant to endpoint, and then finally we're going to measure VF. I guess we could write a step 6 to say that V equals VF minus VI. My mistake. But the V here is really the one that we're going to use mathematically. The VF and the VI are measured, of course, but those aren't really any numbers that you're going to perform calculations with. And yes, I did say calculations. There is unfortunately some math to do. But before I get into the math, I wanted to point out I had another image of a titration. So here is a different situation where our analyte has phenolphthalein as your indicator. And specifically phenolphthalein gets used because the color change occurs so close to pH of 7, but because it's also pretty useful that it's colorless and pink, the suggestion is that the endpoint is at the first appearance of pink. And I have to be a little bit self-deprecating with this. I can't do this very well. I have a really hard time seeing faint pink, but that is the best is faint pink. Now, if you overshoot, it's not the worst thing in the world, but obviously it's not something you want to strive for. That's why typically this will be done in triplicate, where we will take an average in the hopes of minimizing any errors that are introduced through lack of technique. But getting into the math, what fact is mathematically true at the exact moment of neutralization? Going back to our example, I had said that there were 3 possible outcomes, and we're going to focus on the third one. In the third outcome, where they perfectly cancel each other out, that means that the amounts, so two amounts have to be equal, and the amounts are going to be the acid and the base. But I want to kind of morph that a little bit, because those words they're great, they work, but we know a little bit more about what acids and bases are. The word in chemistry for amount is mole, and for acid, the key component of the acid is actually the H+. So we're going to say moles of H+. Similarly, for the base, we're going to say moles of OH-. And at the moment of neutralization in titrations, it's called equivalence. the moles of hydroxide are equal to moles of hydrogen. There we go. But we didn't measure moles, and we don't measure moles. And everything you see in this image isn't a mole. In fact, everything there is a volume. So everything, yeah, and in the steps before, we're going to be measuring VF and VI, and then we need to turn that into a V. All of those V's are not part, those aren't moles. And if we go back to our original definition, there's also this word concentration. So concentration and volume are really what we're dealing with. So there's also some molarities. Now, if we remember, molarity is moles per liter, moles over volume. Let me change that. Moles per liter. Moles of solute per liters of solution, which could be equal to N for number of moles over V. And so we can kind of rearrange that to be that the number of moles is equal to molarity times volume. So if we substitute this in for both places where we see moles, we get what our mathematical titration equation is. At the equivalence point, which is at the end point, based on the color change, and the equivalence being something we're going to calculate, the molarity of the acid times the volume of the acid is equal to the molarity of the base times the volume of the base. Hypothetically, there's a bunch of qualitative evaluations that we can make, but this is really just, I want to call attention and let this soak in. This is our titration formula. This all harkens back to what gets done in the lab. By conducting a careful, exact reaction, we can either measure these quantities or calculate a missing quantity based on the data that we record in lab. It's a very powerful tool. So, I managed to make this animated GIF a couple weeks ago of like walking through the process, and I kind of liked it. So I'm going to let it loop while we work through this. There are two practice problems I want to go through to let you see how this can show up. And then there's one more thing to mention and we're done. So in a titration, 14 milliliter sample of base is titrated by 0.2 molar HCl. The initial burette reading is 10.5 milliliters. The endpoint occurs when the burette has a reading of 19.90 millimeters. What's the concentration of the base? So interestingly, though I made this picture, I completely did this backwards because in this problem, the base is down here and the acid's up here. And there's nothing saying that it has to be one way or the other. But in the actual images, the solution's going from colorless to pink, so of course it's backwards. If I was using phenolphthalein as my indicator, it would go from pink to colorless, which I will tell you I'm even worse at doing. Completely screwed up a lab in college because I couldn't tell when it was colorless. And I was like, oh, is this colorless? And everyone said, no, that's still bright pink. Nice try. Regardless, we should go through really quickly and we should label everything with a variable just to make sure that we have everything right. This is sample of base in milliliters, so that's a volume. And we're going to say volume of base. This says molar HCl, so we're going to label it as molarity of acid. This says initial burette reading, so I'm going to call that VI. And then this says endpoint occurs when the burette has the reading. So that's actually our final. So if we want to plug in MAVA equals MBVB, I'm sorry, I forgot one thing. They asked what's the concentration of the base. That's MB. We've got 3 V's and 2 M's, which isn't quite right. And I'm also kind of looking at it, I'm missing a VA. However, that's where these two numbers come in. VA. I was going to write V analyte, but the analyte can be either acid or base. So in this case, it's going to be an acid. But VA is going to be equal to the final reading minus the initial reading, which is going to be equal to 19.90 milliliters minus 10.50 milliliters. And I believe that should be 9.40 milliliters. So now we have a VA, an MA, a VB, and they're asking about the MB. We have 3 knowns, 1 unknown. That sounds exactly like a titration. So let's plug in. 0.200 molar. This is going to bother me. I have to check my math, because if I did my math wrong in a video, it's going to be like Super embarrassing. Yeah, 9.4. So 0.200 molar times 9.40 milliliters. I know in some cases we said that that volume had to be in liters. Since there's two volumes, as long as the two volumes have the same unit, it doesn't matter if it's milliliters or liters, but they will have the same unit. If we're solving for volume, the units have to match, and I think the next problem will show that to you. We don't know M. I always make it non-subscript. MB. I am doing these as subscripts. M sub A, M sub B. This is 14.0 milliliters. And then we just divide over by 14, multiply and then divide. I'm going to do that really quickly. 0.2, 9.4, divided by 14. And we're going to round to significant digits. I see 3 everywhere, so we're going to round to 3. The concentration of the base, as we've done the reaction, is 0.134 molar. Does this answer make sense? Keeping in mind that these are MA times MAVA equals MBVB. The two are multiplied, but they are equal. This looks a little bit like Boyle's law, that relationship. And remember, in Boyle's law, the two variables are inversely related. This should make sense here. To get a neutralization equivalence, perfect neutralization, the higher the concentration, the lower the volume that is needed. The higher the volume, the lower the concentration is. So in other words, if 9 milliliters of acid and 14 milliliters of base perfectly cancel, that must mean that the acid is more concentrated than the base. That is what we see, so this answer should make sense. And then finally, we are going to calculate, I don't know. No, we're going to calculate. Actually, you know what? I think this one's even a little bit simpler, so I'm going to not talk, and I'm going to give you guys a minute. This one is actually in line with the image. This one is chemically valid to the question, but hit the pause button and figure it out. I'll give you a little time. Excellent. So looking at this, I'm hoping that you got an answer that is greater than 0.25. That should make sense. But let me see that I can actually do that. Acid, so that's VA, that's VB, this is MB. So MA, VA equals. We're solving for MA. I always forget to do that. 10.0 milliliters. Since you're choosing that volume, usually you're going to pick a nice round number because this is the sample, the analyte, is something you're measuring. There's no reason not to pick a reasonable number like 10 or 15 or 5 or 20. It's the 16.7 coming from the burette. That's the one that's going to be kind of crazy. 0.25 times 16.7 divided by 10. Yay, we got a number greater than 0.418. Greater than 0.25, which totally makes sense. Some final thoughts about this. So I've copied over the formula found in your reference tables on table T, and that's here. There's one region where I see usually a lot of confusion or the possibility of people making mistakes. If you consider a 1 molar HCl solution and a 1 molar H2SO4 sulfuric acid solution, keep in mind that when HCl dissolves in water, you get H plus and Cl minus, and when H2SO4 dissolves in water, you get 2 H pluses and SO4, 2 minus. So really a 1.0 molar hydrochloric acid solution is 1.0 molar H plus, and a 1.0 molar sulfuric acid solution is 2.0 molar H plus. So what you will see in lab is if you ever use sulfuric acid, you will need twice as much base as you think you do, in which case, notice that they don't say Ma is molarity of acid, they say that Ma is molarity of H plus. I would suggest making that step. That being said, Most of the problems you'll see on our reagents are going to have substances that have one acid H per molecule, so none of this really matters. But I'm just mentioning it in case it happens because the practice sheet I'm going to include has a couple of problems that might use that. And then as an extension of this, you could actually, if you have a different, instead of using an indicator, if you had like something that measures the pH of your solution, you could actually make a graph of V versus pH, and you can make a neat little curve that shows what's going on. It's called a titration curve. We don't cover them, but I'm just letting you know that there's a vast extension of this. And then you can actually like look at the nature of the acid and what kind of information you can pull from that graph. There is a reason for the jump. I'm not going to get into it. And then also sometimes the indicator you choose isn't always the best choice. Keep in mind that the full neutralization is happening at a pH of 7. If you use methyl orange, which changes color between 3 and 4, give or take, it'll change color and you'll still have an acidic solution. You won't be fully neutralized. So it's always good to pick a solution that has, or pick an indicator that has a change in color closest to 7 to get the best results of your titration. Thanks for watching.